Welcome back to the deep dive. Today, we are dissecting a paper that sits right at the intersection of two fields that they don't always speak the same language.
Not at all.
On one side, you have the probabilistic, the differentiable world of deep learning. And on the other, the rigorous, discrete world of classical sparse approximation.
And this paper, Sequential Attention for Feature Selection by Yasuda and a team from Google Research and CMU, it tries to build a bridge.
It really does.
It's a significant piece of work because it tackles this fundamental inefficiency in how we handle high-dimensional data in neural nets. We're talking about closing the gap between, let's say, heuristic attention mechanisms and the hard guarantees of greedy algorithms.
Like orthogonal matching pursuit.
Exactly like OMP.
And for our listeners who are deep in these architectures, we're not just talking about applying some simple math to your weights.
Right.
This is a fundamental rethink of how feature importance gets calculated inside the training loop.
Right. The core problem they identify is what you could call a redundancy trap. It's inherent in standard attention mechanisms.
That's the starting point, isn't it?
It is. In a standard, one-shot attention framework, think of a concrete autoencoder or even something like Lassinet, the model evaluates feature importance globally.
All at once.
All at once. It calculates the gradient with respect to all features simultaneously. Now, the problem comes up when you have correlated features.
Okay.
If feature A and feature B are highly correlated, and both are predictive, a global attention mechanism tends to just assign high weights to both of them.
Which is incredibly inefficient if you're on a budget, say. You can only pick K features. You don't want two features telling you the exact same thing.
You want the feature that gives you the maximum marginal gain, the most new information, given what you've already selected.
And that's the concept of residual value.
Precisely. Classical greedy algorithms, like forward selection, they get this right because they're iterative by nature. They pick a feature, project the target down, calculate the residual,
and then they hunt for the next feature that best explains that leftover signal, that residual.
Exactly. And standard attention it can't do that. It doesn't have a concept of what's already been picked inside a single forward pass.
So the mission here, the whole point of this paper, is to build an algorithm that mimics that iterative conditional logic of OMP, but to do it all inside a differentiable neural network.
That's it. They call it sequential attention. The whole goal is to keep the computational efficiency of deep learning, not having to train separate models while getting the nice selection guarantees of OMP.
Let's get into the mechanics then, because how they implement this greedy behavior inside a continuous training loop is really clever.
It is. It's a state-based approach. So you have your input matrix X and a vector of learnable parameters, your attention weights, let's call them W.
Okay.
But the crucial piece is they maintain a set of indices, S, which represents the features you've already selected.
And at the very beginning, S is just empty.
Right, it's an empty set. So at any given training step, the algorithm treats features in S completely differently from features that are not in S.
The complement set, SE.
Right. If a feature's index is in S, it's active. It gets passed to the downstream model layers directly, maybe scaled by its own weight.
But the real magic is what happens to the unselected features.
Yes. For those unselected features, the algorithm applies this soft mask. It takes the soft max of the attention weights, but only for the features in that unselected set.
Creating a kind of competitive bottleneck.
It's exactly that. The unselected features are all fighting for the same pool of probability mass. And this uses the Hadamard product, the element-wise multiplication.
Right.
So the actual input going into the network is a mix of the fully active selected features and the scaled competing unselected features.
This structure forces the model to prioritize. Because of that softmax, if one unselected feature gets a high weight, it just crushes the signal from all the others in that unselected pool.
Exactly. And once a feature wins, it gets the highest weight at a decision point. It gets moved into the set S. And in the next iteration, that feature is no longer part of the softmax competition. It just flows through.
Which changes the entire gradient landscape for the features that are left.
Completely. The model doesn't need to use them anymore to explain the variance that's now covered by the newly selected feature. So the attention weights just naturally shift to find the next best piece of signal.
Okay, but implementation-wise, that sounds horribly expensive. If I want Kaigi features, the classic way is train to convergence, pick one, freeze it, retrain.
That's okay full training cycles. For a data set like Criteo with billions of rows, that's
Yeah.
a non-starter. You just can't do it.
So how do they get around that?
This is their one-pass optimization. It's brilliant. They don't train Keiger models. Instead, they just partition the training epochs of a single run into K phases.
So if you have 100 epochs and you want 10 features, you're picking one feature every 10 epochs or so.
Roughly, yes. They solve for the model parameters and the attention weights at the same time with SGD. Then at the end of a phase, they do a hard selection, find the index with the max weight in the unselected set, move it over to S. They might reset the other unselected weights, and then training just continues, no stopping.
So they're basically approximating the train to convergence step with just train for epochs.
Precisely. It is an approximation, but as the experiments show, it's a very, very effective one. It brings the complexity back down to training a single model, which is the only way you can scale this to modern deep learning.
Okay, let's pivot to the theoretical core of the paper. This is, I think, the most impressive part. They don't just propose a cool new heuristic. They prove that in a certain setting, it's mathematically the same as OMP.
This is Theorem 1.1. And to make the proof work, they analyze a slightly simplified version called regularized linear sequential attention.
Right, so they strip out the deep network nonlinearities for the analysis.
And crucially, they remove the softmax. They replace it with L2 regularization on the weights. The claim is that this simplified version selects the exact same sequence of features as OMP would.
Which is a huge claim.
It is. And the proof is fascinating. It's a two-step argument. They don't prove it directly. First, they prove that their sequential attention is equivalent to something called sequential lasso.
And sequential lasso is just applying lasso over and over again.
Basically, yeah. As defined by Luo and Chen, you solve the lasso problem, pick one feature, add it to your active set, and then you solve lasso again on the residuals.
So where does the connection to lasso come from in their attention mechanism? Is it that Hadamard product again?
It's exactly that. It leverages this known duality in optimization. When you overparameterize a coefficient, say beta, as the product of two variables, u and v, and you put L2 regularization on u and v.
The implicit regularization on beta itself becomes the L1 norm.
Exactly. The Hadamard product overparameterization acts as an implicit lasso.
Okay, so step one is done. Their method acts like sequential lasso. Now for step two, proving sequential lasso is equivalent to OMP.
And this is where the real novelty is. Previous work had shown this, but only in very, let's say, nice settings.
The sparse signal plus noise regime, assuming the data has good properties.
Right, assuming the data isn't messy. Yasuda et al. Proved this equivalence in the fully general setting. No assumptions about your data matrix X or your target Y.
Wow. How do they do that? How do they bridge the gap between a lasso optimization path and a greedy correlation search like OMP without those nice assumptions?
To use a geometric argument, it involves something called polyhedral sections. They look at the dual problem of the lasso, and the constraints of that dual problem form a polytope. Let's call it C lambda.
Yeah.
The whole optimization can be seen as projecting the residual vector onto this polytope. And as you relax the regularization, the polytope expands. They proved that the first face of this polytope that the residual vector hits corresponds exactly to the feature column that has the maximum absolute correlation with that residual.
And maximum correlation with the residual is, by definition, the OMP selection step.
Precisely. Because the lasso path has to geometrically hit the polytope at that exact point of maximum correlation, it is forced to select the same feature as OMP. It's a really rigorous unification of the two ideas.
So that means their attention weights aren't just some arbitrary numbers. They're actually proxies for marginal information gain.
They are, and they checked this empirically. They ran an experiment to calculate the true marginal gain, which is computationally insane. You have to train a separate model for every single candidate feature at every step.
But you need it for the ground truth and the results.
The correlation plots are amazing. In the early rounds of selection, the Spearman correlation between their attention logits and the true marginal gain was over 0.9.
That's incredible. It basically validates the whole premise. The soft gradient signals are correctly identifying the features that will give you the biggest drop in loss.
Yeah.
Now, I want to go back to something we kind of glossed over, the softmax mask.
Yeah.
In one of the later sections, they do an ablation study that really challenges whether the softmax is even necessary.
Ah, yes. This gets us to the Hadamard product overparameterization hypothesis. There's a growing school of thought, and this paper supports it, that the real magic isn't the normalization from the softmax, it's the expansion of the parameter space itself.
Meaning that just optimizing a feature's weight, y, is fundamentally different from optimizing two parameters, we and vi, whose product is the final weight.
It creates a totally different optimization landscape. The landscape around 0 becomes more like a saddle point, not a sharp local minimum. This lets gradient descent escape 0 more easily if a feature is useful, or converge to exactly 0 if it's not.
And they tested this by swapping out the softmax, right?
They did. They replaced it with L1, L2, and just an unnormalized Hadamard product. And the performance was nearly identical across all of them. All of those variants crushed baselines, like Lassinet. It strongly suggests the softmax is nice for interpretability. It makes the weights look like a probability distribution. But the actual engine driving the feature selection is the gradient dynamics you get from overparameterization.
That is a huge insight for anyone designing architectures. Focus on parameter factorization, not just activation functions.
It definitely challenges the old attention is softmax idea. Here, attention is an emergent property of the landscape's geometry.
So let's talk about the experimental results. They ran it on standard stuff like MNIST and isolate, but also on some massive industrial data.
On the smaller data sets, it was competitive with or better than state-of-the-art methods like concrete autoencoders. But the MNIST visualization really tells the story.
The clumping phenomenon.
Yes, they compared it to a naive baseline, basically OMP on a neural network, where you just calculate gradients and pick the max. And that baseline totally failed because it would select a pixel right next to one it had already picked.
Because adjacent pixels in an image are, of course, highly correlated.
Right. The naive method sees a strong gradient for a pixel and its neighbor, and it just picks both. It doesn't get the redundancy. But sequential attention showed what they called high adaptivity.
It picked pixels from all over the digit.
A really diverse set. It was effectively sampling the shape of the digit rather than just clustering on the brightest spot.
Yeah.
It understood that once you know pixel xy, pixel x plus 1y, gives you almost zero new information.
That really confirms the residual value logic is working, even in a complex nonlinear setting. Then there's the Criteo dataset, the stress test.
Right. 39 features, but more than 3 billion examples. The key metric there wasn't just accuracy, it was stability.
Which is critical in production. You can't have your feature set totally changing every time you retrain on slightly different data.
And Lasso is famously unstable, but sequential attention showed way lower variance. It consistently found the same high-value features run after run. And performance-wise, it beat the Lasso-based methods once the feature budget got above 15 or so.
Which is a very realistic range for those kinds of models.
Absolutely.
The last experiment I found interesting was the batch selection one, where they tried picking more than one feature at a time.
Right, selecting batches of size 2, 4, 8, and so on. It's a test of how greedy you really need to be.
And the results showed that being strictly sequential, picking one at a time was best.
It yielded the highest quality feature subsets, which makes perfect sense, right? As soon as you pick a batch of size 2, you risk picking two features that are redundant with each other. The algorithm doesn't get the chance to condition on the first before picking the second.
The patience of the sequential approach pays off.
It really does.
So to synthesize this, we have a method that bridges this theoretical divide between sparse approximation and deep learning. It's a differentiable, one-pass version of greedy forward selection.
That is empirically shown to approximate true marginal gain and, just as importantly, has a proof of equivalence to OMP in the general linear setting. That gives it a theoretical foundation that most deep learning heuristics just don't have.
It really legitimizes using attention for hard feature selection, as long as the architecture respects that sequential conditional nature of information.
And it shines a big spotlight on overparameterization as a core optimization tool. Maybe even more important than the normalization layers we usually give credit to.
So I guess we'll leave our listeners with a final thought. If the softmax function is empirically unnecessary here, and the real power is in the Hadamard product smoothing the optimization landscape, should we be rethinking attention blocks in other places, like transformers?
That's the provocative question. Maybe we should rely less on normalization and more on explicit parameter expansion to do the heavy lifting. A really interesting thought.
Indeed. For those looking to implement this, the paper has the full algorithm and the code is available. A must-read.
Definitely. A great tool for any high-dimensional modeling task.
Thank you for joining us on this deep dive. We'll see you next time.